welcome to Daily Planets in the Classroom. I'm Kim Jektiani. We've dedicated the next 1 hour to showing you all the new green sources of energy that's available to us now that global warming is around. We're going to visit Iceland to show you their ambitious plan to drill into the Earth's crust for 10 times more power. It's positively bubbling with potential. But first, the power of the atom. We're about to take you on a rare behind-the-scenes tour of a nuclear generating station. And no, there was not a single donut in sight.
Let's take a closer look. Ah! Okay, here goes. How does the world meet its growing energy needs and at the same time combat climate change? Is nuclear power the solution? Well, on the upside, it's a tried and tested technology and it doesn't produce any carbon dioxide. On the downside, there's only a finite supply of uranium and of course there's the toxic waste to deal with. The reality is that new nuclear power plants are popping up all over the world. This is the Bruce Nuclear Generating Station in Ontario. There are 6 generators active inside. Let's take a peek, see how it works. The whole process begins in here, inside the nuclear reactor. Now, normally there's no way we'd be able to go inside. It would be far too radioactive. But this reactor was closed down in 1995, so it is safe to go inside. Having said that, there is still some residual radiation, and that's why I'm wearing all this safety gear to prevent me getting contaminated. This little device will monitor any radiation I do pick up, and if that level gets too high, an alarm will go off, and that's when I leave. As for now, let's go. The reactor is housed in this vault behind concrete walls 2 meters thick. The only way in is through this airlock, which ensures negative pressure inside the vault, meaning air can be sucked in but not out. So here it is. This is the nuclear reactor face itself. You can see the 480 channels where the fuel bundles go. Each fuel bundle is made up of lots of little pellets of uranium about this big. Now, originally uranium was formed in the stars. These days, the stuff that fuels this is mined in Saskatchewan. But uranium on its own isn't enough to produce electricity. You also need deuterium oxide, so-called heavy water. Uranium is a naturally unstable element, and as each atom decays, it emits a tiny particle called a neutron from its nucleus. If that neutron hits another atom, it causes it to fission or split apart, releasing heat, but not enough heat to make electricity. That's where the heavy water comes in. Heavy water is about 10% heavier than ordinary water because it contains more neutrons. Now, the heavy water flows all around these fuel bundles, and its purpose is to slow the neutrons down as they split from the uranium atoms. Because the neutrons are going slower, they hit more uranium atoms, more neutrons are split off. Pretty soon you've got neutrons flying all over the place as these atoms split, and you've got lots of heat. And when I say lots of heat, I mean lots of heat. All that heat ends up here, where it turns ordinary water into steam in massive boilers located just below this 250-ton steam drum. All that steam feeds into these pipes behind me to turn the spindles encased inside these 3 massive turbines. Now, as these turbines rotate, they spin the generator right down the other end. Here it is, and voila, you've got electricity. The fuel bundles need to be replaced every 18 months. By that time, they're extremely radioactive and extremely dangerous. That's why every day a robotic fueling machine removes the spent bundles and brings them here, where they're stored underwater in this reinforced concrete pool. It turns out that ordinary water is an effective barrier against this radiation. Now, if the water level were to drop and the fuel bundles be exposed, I'd get a lethal dose of radiation very quickly. Needless to say, there are lots of safety measures in place to make sure that level does not drop. The ultimate fate of the waste isn't yet clear. The government is considering storing it underground, but for the moment, Canada doesn't have a long-term strategy for storing its nuclear waste.
This next story shows what scientists can do to help a country shift gears to another energy source that's also very green. In fact, you could say it's bubbling with potential.
It's a country blessed by natural beauty. Iceland may also be the most environmentally friendly nation on Earth, and it's all because of a renewable and clean source of energy underground.
It is mainly for heating our homes, of course, generating power, and it also for the greenhouse industry. And almost in every small village or town in Iceland, there is an open-air geothermal pool. So it is used for our everyday life.
Iceland sits right on top of the Mid-Atlantic Ridge. That's where magma rises from the Earth's mantle, forcing the Atlantic and Eurasian tectonic plates apart. All this leaves Iceland exposed to volcanic activity.
Is our, what shall I say, heat source actually which we are after. There is a lot of heat embedded in the rock under our feet, and we go after this heat.
Enter Albert Albertsson. He's in charge of one of Iceland's 5 main geothermal plants, and it's his job to get as much heat as possible out of the ground. It starts with a series of 7 deep wells that tap reservoirs of water under intense pressure.
The water comes from a depth of approximately 2,000 meters, and the temperature of the water is 243 degrees C. In ground it is water, it's water phase, meaning high pressure. When we open the reservoir, the fluid starts to boil, and that is the driving force of the fluid up to the surface.
What comes up is a mixture of steam and fluid. Once the two are separated, salt is removed from the steam. Although the salt occurs naturally, it will corrode the pipes and machinery if it's left as it is. Then the steam goes straight into a generator where it's used to make electricity. In this case, 80 megawatts, or enough to power a small city. This new energy is now used to heat regular groundwater. It flows through a system of heat exchangers until it reaches a maximum temperature of 115 degrees Celsius. This water is then piped to homes for heating and drinking.
We do it more or less in a sustainable way, and the geothermal energy or the high temperature fields here in Iceland, most of them, we have renewable energy. And we pollute the atmosphere very, very little.
In fact, the only pollution comes from a tiny amount of sulfur and carbon dioxide that are released naturally as the heat rises from the earth. Otherwise, the only thing left over is hot water that flows into Iceland's famous Blue Lagoon.
It is pure water, it is not poisoned at all, it's more than that, it is healthy. It cures a lot of skin disorders, mainly though psoriasis. So it's a great gift.
Today, geothermal energy heats most of Iceland's homes and provides nearly 1/4 of all of its electricity. In the future, Iceland plans to use it to make hydrogen to wean its cars and trucks off imported oil and gas. Although many countries aren't as geologically gifted as Iceland, Albertsson believes the world would benefit from geothermal energy if people would only think deep.
The temperature of the hottest part of the earth is even higher than the surface of the sun. So there is a lot of energy to go after. And I can simply ask, is it more worth to put our money into going into space or going down after this energy in these times?
Barbara Kerr's expecting company. At 83, she insists she doesn't need the wheelchair. It's just a convenience. But she's got to check the chicken. Don't want it to burn. This is the 8th and final version of Barbara's solar cooker. Made with double glazed glass, it can reach temperatures of 230 degrees Celsius. The chicken's been bubbling away all morning, and a few stabs with the fork tells her it's time to take it out.
That's going to be very good. What I have been concerned with is the simplest, easiest to build, preferably with the design that someone who could make it so a dress could make a cooker.
The idea of cooking with just the rays of the sun had been floating around the edge of the Back to the Land movement 35 years ago when Barbara first moved into the high country.
Perfect. am not a natural builder, and I had a lot of trouble doing the angles, sawing the angles, and deciding when they said put the reflector at a 60-degree angle, did they mean 60 from here or 60 from here? You know, I just couldn't figure this one out. I could cook this in a solar oven and it would be delicious, but it's also delicious just as a salad. So I would put little cans of rice in 2 cans. I'd put one in one stove and one in the other, and I would wait and watch it. And the one that cooked the fastest, that was the stove.
Her little house at the top of the hill is only about 300 meters from the power lines, but as Barbara designed it, that's as close as it'll ever get. The house is a 960 square foot cinder block solar mass. Large south-facing windows allow the sun to heat the insulated cement floor as well as the brick walls. There is a wood stove, and beside the chimney there's a large vent hole to let excess heat escape.
As I designed it and put it together, I wanted it to be something that did not have motors, did not rely on electronic equipment. I did make a space for photovoltaic electricity because lights and radio and so forth are that integral to my life.
The house is also designed to take advantage of every gust of wind and every drop of rain. Where most downspouts just empty rainwater onto the dirt, this one catches the runoff and reroutes it to a massive storage tank. But this is just for backup. The main water supply is pumped from a 250-foot well using this 100-year-old windmill. And on the days when the wind doesn't blow, these solar panels power a small electrical pump. But the solar cooker design adapts to a variety of uses.
This is a solar water distiller. This will distill over a gallon a day in the wintertime and about 3 in the summer when we get much more direct sun on it.
The water evaporates onto the underside of the glass and drips down into a trough. From there, it's collected in a tank for drinking. Jim Scott designs and maintains the various systems on Barbara's property, like the solar water heater.
Basically, it's a large solar cooker with a water tank in it.
Yet another adaptation of the cooker.
It's an insulated box, a couple of inches of foam insulation, and the tank painted black inside that acts as a heat collector.
Barbara has had requests from all over the world for information on solar cooking.
All over the world, the forests are going down because of the need for cooking fuel. We didn't realize when we were getting into the beginning of it how serious it was. But I had a man who came from Mali and looked at the stoves, and I didn't know what he was thinking, but he looks at them and he says, "We've got to have the stove. There's no wood left." And that's true. The food has to be cooked. And it's a basic, true need. It's not being frivolous to use wood like that. The necessity is there unless we do some good alternative, and solar is a good alternative.
Her company now sells these prefabricated cardboard solar cookers, a few clothespins and a plastic bag, and voila, a simple, inexpensive solar cooker.
Least amount of resources that each person can use, the more that each person can recycle and reuse and return to the earth. This is where we could make some impact. It's not a technological solution, it's a social solution.
Fighting against the raging sea, this team of engineers is trying to launch a huge steel buoy, or buoy if you prefer, in the Atlantic Ocean. It's called a power buoy, and instead of directing traffic, it directs waves and turns them into electricity. Today the water is rough, and it's making their task almost impossible.
We're basically talking about a technology that will be able to harness the enormous amount of mechanical energy in ocean waves and convert that into low-cost, reliable electricity.
George Taylor's team thinks there's enough electricity in the ocean to supply power to the world. That's why they're putting wave power stations all across the world. This one is in Hawaii.
As the wind blows across the surface of the ocean, the waves accumulate that wind energy. So by the time the waves get to the shore, where the wave power station is, you will have acquired a lot of energy in those waves.
As soon as they do this, we're good. Fred's got both anchor lines out.
To collect the energy, engineers use a buoy. It's similar to the ones that boats use to help them find their way in the ocean. Only this buoy is massive. It weighs 17 tons, the same as some whales.
Well, the perfect waves are the regular waves that continuously come onto the shore. When the waves are too large, storm waves or hurricane waves, then our system automatically closes down because the forces on the system become very large.
The power buoy lives in the ocean about 3 miles offshore.
Are you off bottom yet? Off bottom.
It's powered to the seabed by a heavy chain. That keeps it from drifting, but still allows it to move. The up and down motion of the buoy bobbing on the water creates the electricity.
As the wave goes past it, and that energy, that mechanical motion of the buoy moving up and down on the waves is then converted into mechanical energy and then in turn converted into electricity.
That all happens inside the buoy. Once the energy is converted, an underwater cable makes it available to consumers.
The electrical power that is generated inside this buoy is then taken ashore via a cable, and this would come out of the bottom of the buoy and then would go down to the seabed, where it would join on to the underwater cable, which would take the power ashore and connect it into the grid.
The power buoys exist in groups, creating an offshore power plant that's capable of producing enough electricity to supply a large geographical area.
If you look at a very large populated area like California with 40 or 50 million people, we are able to show that 100 square miles, 10 miles by 10 miles off the coastline of California has enough electricity or enough power in it to produce all of California's electricity.
So unlike wind or solar power, which can take up a lot of space, wave power is much more concentrated. It could also prove to be more reliable.
You can tell 3 days in advance what the wave energy is going to be when it reaches the wave power station. The reason you can do that is you can look at a satellite photograph and you can see what is 1,000 miles out, further out to sea, and that of course will tell you what you will get later on.
Finding an area with good waves is fairly easy, and so the buoy is able to produce electricity 90% of the time. That's why right now testing is happening in both the Atlantic and Pacific Oceans, and very soon both power plants will produce low-cost, efficient energy.
The cost of the electricity will be the lowest cost of renewable power, and we expect within 5 years from now to be competitive against conventional fossil fuel power and below that of wind or solar.
George Taylor expects that in the next decade, consumers could say goodbye to high energy bills as ocean power becomes the wave of the future.
Wow! Whoa! Ah! That's the fact of the matter. Woo! Did you hear that?
The other one to go. Well, ow, ow, ow. All right, at least there's one little pop.
That was actually quite amazing. John Swain is here to explain exactly what happened when he touched that match to that little froth of bubbles.
Hi, Jay.
What did happen?
Well, that was hydrogen. And I thought it would be interesting with all of the hype these days about the new hydrogen economy and what a wonderful thing hydrogen is to think about where do you get it from?
Okay.
So,
as usual, I have somewhat arcane and maybe even archaic little setup here.
Well, it's little bits of junk.
Take me through this.
Okay. Let me blow some of this out of the way so you can see. This is a pot of water. Yep. I've just used regular water. I could have, in principle, changed the chemistry and made this go a little quicker with some salt or something, but this is just plain old tap water. Yep. Those two little black rods in there, they're carbon rods that I took out of an old dry cell battery. You can see one of them used to be longer, but I broke it. So these are the old ones, not the alkaline ones. Okay,
Yep.
it's a little lump of carbon. I'm picking carbon because carbon isn't very reactive. I could have just had metal wires in there, but then the chemistry gets more complicated.
Okay.
So I got 2 little pieces of copper in there, and I'm putting some electricity through.
Carbon.
Yeah.
Yeah.
Oh, sorry, carbon. Thank
Yeah.
you. And the red one's the positive charge and charged side, and then the black one is the negatively charged side. And this is water, and water is, as you know, H2O.
Yep.
And those are the hydrogens and the oxygens are stuck together by, if you like, an electrical force. That's the chemical bond. And I run some electricity through, and I pry those apart, and the hydrogens are a little bit positive, and the oxygens wind up a little bit negative.
And so they go to opposite.
The opposite ones.
So they go to the 2 different carbon rods.
That's right. So on each one you can see little streams of bubbles forming and rising up to the surface. And so on the negative one here, you get the positive hydrogen ions, as we call them.
So those are little
charges
bubbles of hydrogen coming up.
Yeah, there's little bubbles of hydrogen. And I put a drop of washing up liquid onto the surface so as to have a way to trap the gas. So instead of it just coming up and making bubbles that burst on the surface, you trap them, and after a while you build up a bunch of hydrogen, maybe a little of the oxygen as well, but I'm mostly trying to grab the hydrogen. And then you light those bubbles and you...
So are you saying, John, that this little setup here, scaled up millions of times, is how we would generate hydrogen for what you call the hydrogen economy?
Yeah, that's exactly right. Hydrogen, the reason everybody says isn't this a clean fuel is when you burn it, that means when you combine it with oxygen, you get water. You combine hydrogen plus oxygen, you get H2O, and it's clean. Hydrogen in turn, you have to make. You don't go get it from somewhere, you have to make it out of water. There's no hydrogen mines, there's no, big hydrogen deposits you can go get.
Yeah.
You actually have to make it. That makes the hydrogen a very different fuel from the ones that we're used to, the fossil fuels, coal or oil, because it's not something that's out there, it's something you make so that you can burn it later. It's a convenient means for transporting energy in a very clean way.
And this is nicely cyclical, because you start by splitting up water, and you end by combining it with oxygen to generate energy and make water again.
That's right. And so it is in many ways an absolutely ideal fuel. It's the cleanest thing you could possibly want. It literally, I mean, as people say, you can drink the exhaust out of your tailpipe.
Very neat. So you could, if you had years and years, you could make enough hydrogen here to fuel your car.
Yeah. But there's a very good lesson as well in here, which is that very, very small amounts of hydrogen correspond to rather large amounts of energy in the usual sense in terms of electricity. So to make a little bit of hydrogen, you've got to use electricity for a long time. But then it's a very dense, compact way of carrying that energy around with you, which is why it's nice to have as a fuel instead of, say, batteries or something else. It's a very, very efficient way of moving the energy around. But it's not a fuel as a raw material. It's one that we make, and then we use it for something interesting and return it back to the water from whence it came.
Very neat. Nice demo. Thanks,
Dave.
John. John Swain, physicist at Northeastern University in Boston, Massachusetts. When it comes to new, greener energy sources, there is nothing greener than the source in this next story. Sound intriguing? Well, it intrigued us too. Take a look. Power plants are the pistons of modern civilization. They also drive our need for limited natural resources, and they emit up to 40% of the carbon dioxide that we release into the atmosphere. Scientists like Brian Wilson are looking to an unlikely source to help clean up the mess and keep our engines running.
This is microalgae. It's what we think can be the fuel of the future.
That's right, algae. This green soup of pond scum is one of the fastest growing plants on Earth, and it feasts on carbon dioxide.
It's really as simple as bubbling stacked gas through the water. The carbon dioxide is water soluble, and that fixes it in a form that's immediately available to the algae.
All that feeding produces lipids, oils in the algae. Those can be harvested much like soy and canola and turned into biodiesel. But algae don't require the amount of land or energy of traditional crops.
We can produce fuel at perhaps 100 times higher production per acre than we can with standard oil crops. And so we can materially have an impact on global energy supplies. At the same time, we can immediately extract the carbon dioxide from power plants.
In the 1990s, the National Renewable Energy Lab's aquatic program tried to grow algae at large-scale outdoor circular ponds called raceways. but the growth stalled due to evaporation and invasive species. Jim Sears, a Colorado inventor, came up with a better idea.
Jim's concept was to grow the algae in large plastic bags. That allows us to maintain a monoculture, but at a very low cost.
In 2006, Colorado State University and Solix Biofuels unveiled Mercury One. It's a self-contained system for growing algae, a photobioreactor.
In their normal metabolism, algae don't actually accumulate a lot of lipids. We can apply stress conditions that signal the algae to consume the internal carbohydrates and use those to produce lipids.
These plastic bladders use giant rollers to circulate the algae and thermal blankets to control the temperature. It was an important first step.
One thing that we know from looking at the response of algae to light is that they can undergo photoinhibition when they get high light levels. In fact, even at 15 to 20% of full noon sunlight, we can start to lose efficiency.
So they went back to work and built their Mariner prototype.
The lights here mimic the sun. We provide carbon dioxide from just a canister in this case, not from the power plant's smokestack directly. Air is provided for the bubbling, and we do a pretty good job of being able to simulate the system in this reactor.
The key improvement is in the bags.
If you look in here, we have extended surface areas, so light is coming in from the top, and it doesn't really strike the tubes directly. It strikes them at an angle, so we get much lower light intensity entering the bag, but it enters over a much larger surface area.
And that means more fuel production.
Based on our current production numbers and cost estimates, we believe that we can be competitive with crude oil at $50 a barrel. That's US dollars.
Even the leftovers of the algae have value. Those oils only make up about 30 to 40% of the mass. The rest can be fermented into ethanol or end up as methane, a natural gas. It could actually power a plant. But don't think this is science fiction. Companies like Green Fuel are already running their bioreactors next to an Arizona power plant. If this prototype is successful, Green Fuel hoped to produce 32 million gallons of biodiesel annually by 2008.
What I now know about algae is that this simple, common, single-celled organism potentially offers the key to solve some of society's largest problems.
On tap next for Brian and Solix, beer. Their first commercial test bed will be feeding their algae CO2 emissions from the local brewery.
I definitely have a newfound respect for our tiny green friends.
When you want to go green, you can either recycle or just cycle. And a little help from the sun to move you along doesn't hurt either. Self-confessed dreamer and amateur inventor Peter Sandler has pedaled his solar bicycle into reality.
The reason I started with a bicycle is because it was relatively inexpensive to develop something that would instill some environmental initiatives. And what I thought of was how to generate power not only through self-propulsion, but with the aid of electric motors.
It's a pretty simple idea. You put an electric motor on a bicycle and have the sun charge the onboard batteries. But Peter's bright idea was chained to the shelf for 10 long years until this was invented.
Basically, if it wasn't for the flexible solar panel, there wouldn't be a solar electric bicycle. When I discovered that they did exist and said this would be the opportunity to install these in the bike and make it work. And that's how it all happened.
Now Peter had the new flexible solar panels. His next problem was where to put them on the bike.
I looked at the racing bikes that were used in the Olympics. And you noticed the racing bikes had those black inserts. So I thought, by putting the solar panels in the wheels, I felt that this would be a very cool type of bike to ride around the city.
Sure, the wheels look cool. That's the easy part. But Peter has to figure out where to put the battery's motor and wiring. All this on a bicycle.
The prototype was developed with certain things hidden for a good reason. In terms of the battery, I enclosed the battery to make it waterproof. The controller, which is one of the most important parts of the bike, is also encased in the rear of the battery.
Looking a little bit like an axle on steroids, this compact electric motor drives the front wheel of the bicycle.
The motor, as you can see, it's in the front wheel, but it's also encased with the solar panels. Many other attempts have been made to develop solar electric bicycles, but no one has attempted to do it within the framework of the wheel itself. And that's what makes this bike unique.
The instructions for this bicycle are simple. Sun shines, batteries charge, you turn the key, motor moves bike, ride, and repeat.
It's a very simple process. The sun's rays shine upon the solar panels. They absorb the energy from the sun's rays. The energy then is transferred into the batteries. The batteries then transfer the power to the motor. When you turn the key on and turn the throttle on, you have immediate power, obviously, from the energy that is stored in the battery. And that's how the bike works. It's quite simple.
Right out of the box, the bicycle's batteries can be charged using a wall outlet. A 6-hour charge will get you moving, or just ride it and let the sun do the work.
The bike is a lot of fun to ride. It goes at speeds up to 30 kilometers an hour. It's an eye catcher. People love to see new ideas in bikes. They love the idea of the solar panels. They think it's great. And they don't see the motor, so they come up to me and say, "How does this thing work?"
Peter really is just a one-man show. He's not a scientist or an engineer, just a regular guy who has a great idea to help ease the impact on the environment.
I think I am making a difference. I think I'm making a difference by exposing the fact that there are different forms of energy. I think that this might entice people to further develop solar energy. Listen, a little guy with no degrees who can develop something like this and put it into motion.
Using the power of the sun, Peter Sandler is cycling his way into a brighter future.
Wow! Whoa! Ah! That's the fact of the matter. On Fact of the Matter today, global warming in a glass of water. There's a connection. John Swain is the guy to make that connection for us. Hi.
Hi, Jay. How's it going?
Good.
So let's take a glass of water. I just pour out cool glass of water, and you look at it, and what you'll see is, so look at that.
Yeah, hold it up against my shirt so we can see.
Big surprise, you see a glass of water. But I poured one of these out, about a half hour ago or so, and it's warmed up to room temperature. And now if you look at it, you see something else.
Oh, tiny bubbles.
See the little bubbles?
Yeah,
those little
clinging
bubbles,
to the walls of the glass, right?
Those little bubbles are air that was dissolved when the water was cold, and as it moved up to room temperature, just a couple of degrees, came out. So air is more soluble in cold water than it is in
And
warm
as the
water.
water warms up, the air actually comes out of solution, makes actual bubbles.
Makes actual
and
bubbles.
those bubbles are on the walls, but I guess a lot of it is actually
Some of it
escaped
comes
totally.
out. Sometimes you need a little place for the bubble to start growing, so they'll get little irregularities on the side where they'll find a little place to sort of grab a hold of. There's another place where you see this really dramatically, except a lot of times one doesn't think about it, and this is on the stove. So here's some water. It's been warming up. It's really nowhere near boiling. I can put my finger in here. It's really comfortable. This is only tepid.
Yeah.
And yet, you
Look at
can
all
see
the
there's
bubbles,
lots of little bubbles. Those aren't steam. This isn't water boiling. This is air that's come out because the water's got warmer.
So you warmed it up a bit from the tap to room temperature, some air came out, and then from room temperature to a little bit warmer, more air
That's
comes
right,
out.
even more air has come out. Now, this is something that's got, a good feature and a bad feature. The good feature is, say you're having a party and you'd like to have relatively clear ice cubes.
Because I know everyone that comes to a party, I have to demand that.
Right, so we got a couple here. You can see these were made with
Can I
water.
dump these, dump these
tip
out?
some out. So these, okay, so these were made with water that was, it was just water out of the tap. Okay, this is water with a lot of dissolved air inside, and as it froze, bits of air were trapped inside, and you see this
So
cloudy
one
thing.
like that is completely cloudy.
Yeah, and on the other hand, I'm going to tip these ones out.
Sure.
And here you see, okay, some of them are dirty on the edges, but there you see one that's quite clear. So in this case, you can see a little cloud inside. That's probably bits of mineral that were left inside, dissolved. If you want really, really clear, you'd go for distilled water. But the idea is, if you start with the hot water, the air's been largely driven out, and then when you freeze them up, it won't be trapped inside. You'll get a clear ice cube.
So at every step, as long as you warm the water, you're getting less air dissolved
That's right,
in
you're
it.
getting less air dissolved in it.
Now you said
okay.
there was a bad side too.
Yeah, there's a bad side to this, and it's tied to global warming. You know, a lot of people think, okay, global warming, actually, what's so bad? You know, I'd like it if the lake were a couple of degrees warmer.
Yep.
I'd like it if the river were a couple
Better
of degrees
swimming,
warmer.
that's
Better swimming, great time for me. Problem is, there's things that live in there, like fishes, that rely on dissolved oxygen, dissolved air in the water to be able to live, to breathe. You raise the temperature a little bit, and you can't dissolve as much air in. And now you run the risk of suffocating these things. So it's a
Because I'm sure most of them are finely tuned to that level of
They're
oxygen.
pretty much just getting by. Most things are kind of doing okay. If you drop the pressure off just a little bit for you, you'll notice, you know, life gets a little bit rougher. So it's a really big concern. If you go places like close to a power plant, for example, that discharges heat into the water, the fish populations are different, and a lot of them just won't be able to survive. And it only takes a few degrees to drive a significant amount of air out of water. So this global warming can have a huge impact on things that live in
And
the
it's
water.
not something that people would think of. They think the temperature's going up, that's all.
Yeah.
They don't think of air being dissolved in water.
The whole thing, everything is very subtly interconnected. And so you think, okay, it's just temperature. It's not. It's a matter of life and breath, if you like, for the fish.
Thanks, John.
You're welcome.
John Swain, physicist at Northeastern University in Boston, Massachusetts. Now, if you're somebody who spends a lot of time cooking in the kitchen, you know how much hotter that kitchen can be compared to other rooms in your house. Well, in a restaurant, it's even hotter. Just think how much heat is wasted just going up the exhaust vent. And you know what? That does not have to be the case.
5 out, coming in.
One no milk. That's another entree.
Just ask someone who works there. A restaurant kitchen is extremely busy and very, very hot.
In a commercial restaurant kitchen, there's an excessive amount of heat. Just these stovetop burners are generally 25,000 BTUs apiece. There's more heat being generated on this stove than in your average house's furnace.
Now, a Canadian company called Martinair has a new way of grabbing that heat and using it to save money and help the environment.
On a restaurant kitchen, it's like the furnace is on all the time. From the time they open till the time they close, it's like never turning off the furnace in your house. And all of that heat is going up the exhaust stack 16 or 18 hours a day.
In a restaurant kitchen like this one, the amount of heat going up the chimney is staggering. While the chefs work on their masterpieces, 8,000 cubic feet of hot air is exhausted every minute at 110 degrees Fahrenheit, 43 Celsius. For Martinair, it seemed like a red-hot opportunity.
When you exhaust as much air out of a restaurant as they do, you have to replace that air, and that air is coming in cold. So what we're able to do is extract the heat from the exhausted air and transfer it to the incoming air.
The system begins right over the stove. Hot air and smoke rise from the stovetop into a standard restaurant exhaust hood. But the air isn't clean. It's smoky and greasy.
The problem with grease in the exhaust airstream is that the grease could clog whatever type of recovery device is being used, and that's a problem that's been around for as long as people have thought of the idea.
But Martinair found a way around this problem, literally.
The way that grease is extracted is by changing the direction of the air. The air turns corners very quickly, and if you can turn the air quickly enough so that the air makes the corner but the grease doesn't, you can extract the grease and keep the recovery system clean.
But the guts of the system are up on the roof.
All that heat from the cooking equipment down below comes up through this duct, but before We let the hot air go out into the sky. We bring it into our energy recovery system.
The recovery system works something like a car radiator. The hot air passes over pipes filled with glycol fluid, heating it up fast. The hot fluid is then fed through a series of coils that are used to warm up the outside air before it goes back inside. That means it takes a lot less energy to keep your customers not only fed, but warm.
In this restaurant, about 115 tons of greenhouse gas emissions are being saved in each restaurant that's equipped with this system.
Jeff's customers are impressed too. This Canyon Creek is one of 40 restaurants owned by Surcorp. 15 of those now use the heat recovery system.
We're pretty confident that the last couple of restaurants we've opened, both Canyon Creek and Jackassos, will be the most energy efficient restaurants in Canada.
And results like that are more than just hot air. Imagine a job where you're paid to watch grass grow in a painstaking way. It doesn't sound very exciting. Even the people doing it would admit that. But what they're doing might just offer insights into the future of a warmer Earth. It's a little patch of land in Northern California with a twist. It's proving to be fertile soil for groundbreaking research about global warming.
Looks like we're getting a good canopy now. Leaf area index is probably up to 1 to 2.
For Chris Field, this grass is as good as a crystal ball.
We think of the Jasper Ridge grasslands as kind of a model ecosystem. It's a window through which we can get access to the important responses that underlie the changes you might see in Arctic tundra or in Amazon rainforest.
The Stanford ecologist and his team of researchers have been poking and prodding and analyzing this unassuming plot of land for a few years now. It's been telling them, expect the unexpected when it comes to climate.
We were surprised by the findings. We thought that in general, the plants would be happier and they would grow more under the global change conditions, but under a wide set of conditions, they did not. In fact, the plants were less happy.
Before this study, most people thought carbon dioxide emissions would actually benefit plants, making them grow bigger and faster. This study has turned that idea on its ear. And it took an unprecedented experiment to reveal it, one that looked at more than just CO2.
The way we simulate global climate change at Jasper Ridge has four components that we expect to be part of a wide range of futures, not only in California, but around the world.
They added warmer temperatures, increased nitrogen from pollution, and increased rainfall to the equation. Then they watched the grass grow. For the experiment, 36 plots of grass were divided into 4 quadrants. Most of the instruments and sensors you see here are buried.
What we're finding with this experiment is that most of the action is below ground in terms of responses to global change.
To simulate various conditions, one quadrant might have elevated CO2 and nitrogen, but normal water and temperature.
See how much darker the green is here than it is in the adjacent quadrant. That's
quite
not
striking.
Setting it up is the easy part. The hard part is collecting data without destroying it. So research coordinator Nona Chiarello had to find a creative way to monitor the grass.
What I want to do is take an image of the soil below ground where I can see all the roots growing in the soil, and I want to be able to do that throughout the growing season in order to monitor how much root growth there is as a function of different treatments and how much root death there is.
She slips this scanner into the plastic tube, rotates at 360 degrees, and creates a 3D picture of what's happening at the root level. She also uses something called a spectrum to check the progress. This fiber optic reader can tell how green or lush the plants are at any given time by measuring the light reflected from a small area of land. Now you're probably asking, what could be more exciting than watching grass grow over a long period of time? How about watching it grow second by second?
Plant growth is limited by many things, and when we add extra CO2, we expect plants to grow more because that's one thing that limits their growth, but there are all these other limitations. And by measuring instantaneously, I'm able to see on a second-by-second basis that in fact they're not actually taking up more CO2 and growing more.
Every second, sensors send data to this machine about how the plants are responding to the changes in temperature, nitrogen, carbon dioxide, and water. And that information is then streamed live to the lab. It's here the grass finally becomes that crystal ball.
So basically, this is a part of the processing activity that gives us the comprehensive understanding of how the ecosystem works and how it's going to work in the future.
And it's telling Chris that the grass of the future will not be greener.
My personal feeling is that California 100 years from now will be a worse place in terms of the grassland ecosystems. It's likely to be dominated by weeds, and it's likely to be more variable from year to year. Kind of an ecosystem where you wouldn't want to go for a hike with your dog.
This is what the Amazon looks like when it's on fire. It's the world's largest rainforest, and yet every year, fire rips through the Amazon, changing the face of the landscape. This particular fire is being deliberately set by Dan Nepstad. He's the man behind the camera.
I think it's actually quite a big deal.
Dan's not a pyromaniac, he's a tropical forest ecologist. He's been living and working in the Amazon for 23 years.
Many lines of evidence point to a drying trend in the Amazon, both with global warming and from deforestation itself.
By setting these fires, he's hoping to find out how the Amazon will respond to global warming in the future.
It's clear that as drought becomes more severe in the region and more frequent, that one of the ways in which forests are going to decline is through fire.
Every year, the Amazon suffers from at least 4 or 5 months of extreme drought, killing the large canopy of trees overhead. Without those trees, the interior of the forest dries up, making it more vulnerable to fire.
Now we know, for example, that by the year 2050, there will be much less than half of the forest remaining, and much of it will have gone from dense, lush rainforests into sort of a scrub, dry, scrub, fire-prone vegetation. And that's a very scary scenario.
It's scary because these trees store about 50 years' worth of the world's carbon emissions. When they're destroyed, they release those gases into the air, and that speeds up global warming.
Really, we have to think about this forest as if it were a giant air conditioner, because all of the water that evaporates off the leaves of those trees is absorbing energy. And as every time we cut down another acre of that forest, there's more energy in the environment, more energy that can heat things up and that can perhaps change the circulation of the great climate systems of the world.
Except one of the biggest mysteries of the rainforest is that carbon dioxide isn't only in the trees, there's a huge amount of carbon in the soil. Today, a team of scientists is trying to take the pulse of the Amazon to see what's happening beneath the surface.
The soil is really one of the big repositories of carbon in the world that could send a lot of carbon dioxide into the atmosphere, potentially accelerating global warming. So we do a lot of work on the soil, the moisture content of the soil, and how that influences the amount of carbon dioxide that's released from the soil, in what we call a soil respiration.
In the lab, scientists can predict how much carbon dioxide leaves the soil based on different degrees of drought. They're also testing the soil to find out how these more frequent fires will factor in. Setting fires is dangerous and detailed work. Long before any flames ever touch the ground, extensive planning takes place.
It takes several months to prepare a forest plot for burning. We have to map out all the trees. We have to determine how much fuel there is, how many layers of leaves there are above the forest. That takes our team of 18 field technicians 3 months, really, to prepare a site for burning.
On the day of the burn, each team member has a specific job. Some take measurements of the fire, others watch for things like animals leaving the area. None of this is easy. The flames are intense, the smoke thick.
I've had times when I'm in the forest and I feel like I'm not going to make it to the clearing because there's so much smoke coming into my lungs.
The fire burns for about a day, then researchers look for clues in the charred remains.
When the fires go out, then we have to go back into the forest, map out exactly where the forest burned, see which trees were scorched and therefore will die, and then we look at the whole process of reinvasion of that forest plot by the insects, reptiles, and mammals and birds of that region.
Using this data, scientists hope to paint a picture of what the Amazon will look like in the future.
There's still huge questions that we just don't know the answer to. For example, how is it that almost a half of this giant ecosystem can be so green and exuberant, have so many species, even though it's subjected to 4 or 5 months every year of brutal drought? But I'm also very much intrigued by the fact that there's still time to do something in the Amazon.
The chance to understand global warming's effect on the Amazon, and in turn the Amazon's effect on global warming, is what keeps pushing Dan. If he can help preserve what's left of the rainforest and protect its future, then when the smoke clears, maybe the Amazon's future will be brighter.
It's cold and desolate and utterly beautiful.
This is probably some of the most exotic terrain on the planet. In a different way, of course, than the tropics, but oh my God, the natural beauty is awesome.
Antarctica is one of the last wild places on the planet. Doug Martinson is part of a team studying the climate and creatures at the bottom of the world.
The atmosphere there is going up through the roof. It's 5.5 times, almost 5.5 times the global average in winter.
Doug is tracking the subtle and not so subtle changes in the waters around Antarctica. But where once he had to travel to the Antarctic in a big research vessel, he now counts on this little submersible to do a lot of the dirty work. This is the Slocum Electric Glider. While Doug sits in his office in Columbia, his collaborators down the road at Rutgers University keep the glider on course thousands of miles away. They can do that thanks to satellite communication.
I can be sitting at my home with my family having dinner and get text messages on my cell phone and know that the glider is okay off Antarctica or off the Baltic or wherever we may be flying.
Flying? You heard right. It may be in the ocean, but it's truly aerodynamic, and it really does glide, like a glider in the air.
Unlike most unmanned underwater vehicles, which use propellers to move through the ocean, the glider uses buoyancy.
Here's how it works.
The pump here is what sucks seawater in through the nose, and that's what allows the glider to get heavy and light, which is the basis for how it moves. When it sucks in that seawater through this hole here, gets heavy, these wings on either side of the glider is what turns that vertical drop into forward motion. For steering, it uses the rudder on the aft end of the tail to go to the desired bearing.
After 3 hours, it comes to the surface, sends all its information back home. If we want it to change where it's going to go next, we tell it at that point. Otherwise, it just continues on its merry way.
The glider is set up to take the same measurements over and over, all along the Antarctic Peninsula.
All the gliders that we have deployed around the world are equipped with a sensor called a CTD. That sensor stands for conductivity, temperature, and depth. This is an example of temperature data coming back from the glider. And what you can see are 4 distinct areas. There's this deep blue, which is sub-zero temperatures, this warmer water up here at the surface, and then some intermediate water masses.
The conductivity measurement reveals the amount of salt in the water, or its salinity.
We can see fresher water, the blue, near the surface, and saltier water, the red, near the bottom.
Doug Martinson uses these measurements to follow ocean currents.
We fingerprint water according to its temperature and salinity. Certain waters that originate in certain places of the earth have very unique signatures. And we can actually use that signature and trace a water mass around the world.
One of the novel things about this vehicle is this section right here. This is the science payload. Underneath, as we rotate the glider, we can see the optics sensor. So these are the 2 pucks. One measuring backscatter of light at red, green, and blue, and the other one measuring fluorometry, giving us an idea of how much biology is in the water as the glider makes its way through the ocean.
The biology they're looking for is chlorophyll, the foundation of the aquatic food chain.
What we can see is the deep reds are where we see more biologic material. It's centered in a band that goes from the surface to about 60 meters deep, and it varies as the glider makes its way along its path.
The glider takes all these measurements at 200-meter intervals. Scientists can connect the dots to get a picture of climate change.
I'm just sitting there looking on the monitor going, wow, look at this. We just got 20 profiles in 3 hours, and 20 profiles from a ship would take me a lot of days on the ship.
Of course, it's not all smooth sailing, even for a glider. After all, this is one of the most hostile environments on Earth.
We can't control that. All we can do is have the mechanisms in place so that we can handle whatever the environment may send the glider's way.
Josh Cohart and his team got a taste of the challenge on the very first day of the mission. It was Sunday morning. The Rutgers team was following the glider via satellite.
Everything went very well through the morning. We all left around lunchtime.
Then Josh's colleague Hugh got a call on his cell.
That text message was one of the concerns that we have in these deployments. It indicated that the glider had a leak.
Hugh got on his computer to take control of the glider and get it to the surface. Meanwhile, Josh called Clayton Jones, an engineer with Webb Research, the company that designed the gliders.
Yeah, we got a leak.
He was in the Antarctic to oversee the deployment.
He took the glider apart and found that there was about a teaspoon of water. So it wasn't much water, but that was enough to trigger that leak detect. He then took parts from another glider that we had on board, replaced the aft section. 2 days later, we had another vehicle ready to go and in the water, and it's been flying ever since.
Flying and collecting data.
It's dramatically changing our ability to do science down there and understand how this system works. So it's just phenomenal for us. It'll just change everything.
Now that's cool.
Wow! Whoa! Ah! That's the fact of the matter. Fact of the matter today is all about global warming as seen in the kitchen. And John Swain is doing the demo. This is very curious. That thing is full, you know that, eh?
Jetting it right up to the brim, almost about to spill over.
Okay.
And this
What's
is a
this
model.
all about?
It's a model for global warming, and in particular, about should you be more worried if you lose North Pole ice or if you lose South Pole ice?
What's the difference?
Well, the difference is actually pretty spectacular. Let's have a look. I'll do a little demo here.
All right.
Put some ice in. You can see here's ice that's actually floating in water.
Right, like an iceberg.
That's right, like icebergs. This is like the ice that's like around the North Pole, for example, aside from what's sitting on Greenland. And the ice is actually a little bit less dense than water. It sort of expands up when it freezes, and that's why it winds up floating. Now, as the ice melts, it will wind up shrinking, and it shrinks into just the space that's below. So it will shrink into that little space, and in fact, the water level doesn't change at all.
Oh, that's sort of neat. So that bit of the ice cube or berg that's above the water kind of disappears,
That's right.
and then the ice is turned into water.
That's right, and it perfectly balances out exactly so that the water level stays just the same. Now, on the other hand, imagine you had some ice that was sitting on land. This would be more like the Antarctic, right?
Okay.
The ice is sitting on top.
So with glaciers on the land surface of the Antarctic.
As opposed to floating ice.
Right.
So this stuff actually melts. Of course, it just turns to liquid and it pours in, and of course the water level rises. So it means while in the northern hemisphere, obviously it's bad for polar bears if the ice starts disappearing, it doesn't do very much to the level of the ocean. On the other hand, southern hemisphere ice in Antarctica, for example, that's particularly bad. It's bad for penguins, but it's especially bad for the level of the oceans because that's really pouring fresh water in.
So in the north, we're talking about ice that's there on the surface of the Arctic Ocean.
That's
so it's
right.
already in. It's already floating.
So there's an enormous difference between floating ice, which when it melts doesn't change the water level, and ice that's sitting on the ground supported by something solid, which when it melts really will change the level. And if we look over here at this demo, you remember this was filled right up to the brim.
And there was tons of ice.
The ice
now
is
there's
pretty much
hardly
gone
any ice.
On the hot stove. The global warming has taken place. This is the northern Arctic sort of area.
Yeah.
And you see the ice has disappeared.
And there's been no change in the level.
Hasn't shifted. We're right up to the brim. Not one drop has slipped out.
Very neat. Global warming in the kitchen. I like that. Thanks, John.
Cheers, Jack.
John Swain, physics professor at Northeastern University in Boston, Massachusetts.
Well, that's it for this edition of Daily Planets in the Classroom. Thanks for watching. Hope you learned something. I'm Kim Jek. The end.